Okay, thanks, and hi everyone. Yeah, as said, I'm going to be talking about survival analysis and how we're using it at Tails to understand lifetime value and customer retention. So, just a brief outline of the talk. I'm going to introduce myself, tell you a little bit about Tails and who they are if you haven't heard of us, and then mention lifetime value and retention, and then go on to the survival analysis bit and how we're using this to model all of these things. Cool. So, hi, this is me, obviously. Before being a data scientist at Tails.com, I was a mathematician. I did my undergrad at York. I did my PhD at Bristol. I didn't go straight into data science. I was actually working as an analyst at the Department for Education for a while, modeling policy spending and participation impacts in education. But then I got more and more interested in Python and what you could do with the language, along with data, got into data science through an ASI internship, and I've been at Tails for the last year and a half. So, who is Tails.com? In fact, has anybody heard of Tails? Excellent. Who has a dog? A couple of people. All right, tough crowd. So, anyway, we are a tailor-made dog food subscription service. So, if you have a dog and you are a Tails.com customer, every month to your door, we will deliver you a tailor-made dog food blend, which is specific for your dog at that time and how old they are. So we do this by getting you to fill in an online consultation with us. When you sign up, you tell us all about your dog, their breed, the health conditions, the previous food, the flavors they like, the age. All of these things go into helping us understand what dog food it is that your dog really, really needs. We package that up. We send it to your door in a bag with your dog's name on it, because really it's for them, not for you. And each month we'll just keep sending you food as long as you're a customer. And as your dog ages, their needs change, the food changes with that. So you don't have to worry again about what food you should be feeding your dog. We take care of all of it. So just as in some numbers then. So we've currently got roughly 85,000 dogs, which is about 1% of the UK dog population, which equates to 4 million meals a month that we're feeding, which is really exciting. It's £24 if you're a customer on average. Obviously, that varies massively because dogs vary massively in how much they need to eat. We also do treats and wet food. One of the cool things is because our food is tailor-made, we have a blend algorithm which determines exactly how much food your dog needs and all the nutrients and everything to create the perfect blend. So we're searching roughly 1 million blends in real time to generate your food. And we are growing fast. So target is we're going to have sales exceeding 20 million this year. We currently have 100 employees in total. And we also have 25 office dogs, so which are very much, very much part of the family. We are hiring, so remember this slide when we get to the end of the talk. Cool. So, customer retention and lifetime value then. So this talk, as I said, it's about survival analysis and the retention side of that. I guess it could also equally be about how when you're going into a techie but not directly data science-y startup as the first data scientist, and how you can get some really great, successful data science products, really value-driving projects that you can work on that are really going to get used. And lifetime value has proven to be one of those things. So why do we care about lifetime value? So lifetime value, as a subscription business, it tells you for each customer essentially how much value we think that you're going to generate for us over the amount of time that you're going to be feeding Tails. So if we have a good understanding of lifetime value, we can use this to look at product giveaways. Maybe we have an offer and we will have some free sample. We want people to try things. We obviously have to scale the things we want to give away relative to the value of the customers attributed, because otherwise, essentially, we're going to lose money and eventually go out of business. And refunds as well. So obviously, if you've had a bad service and you think you deserve a refund, how generous we allow ourselves to be you could also use lifetime value as a metric in that. And marketing spend. It's obviously acquiring customers is expensive, and so it's a case of we don't mind as much. Like we can afford to spend a little bit more money acquiring the customers that we really think are going to love Tails. So it's a good way to tailor the spend, and also project prioritization. Everyone's got a new feature that they want to add or a bug that they really want to fix, but the amount of time that we should be spending on all of these things should be relative to how much actual value we think that this is going to generate for the company. Because if we spend our time chasing tiny margins, and then we're never going to grow and be successful. And I know this is all kind of turning everything thinking about profit, but it's important as well, right? Because obviously we're here because we like dogs and we think they deserve a tailor-made service, and so the more successful we can be, the more dogs we can bring into feeding tails, and so the more we can change the world of pet food. So this is really what we're going for. So our lifetime value model is essentially built out of 3 components, which I think is kind of standard, and we sort of, the way I built it, each 3 of these things kind of works independently, and then we aggregate them together to get the total value at the end. So obviously it's retention. So how long we think you're going to be a customer obviously determines how much value we can get from you. Your frequency, how many orders we think you're going to get. We'd like you to order every month, but obviously some people will pause or delay or move their orders around, so this is obviously taken into account. And order value. So the bigger your dog, the more stuff you buy, essentially the higher your order value, and again, this is a big part of your lifetime value overall. So today, I'm just going to talk a little bit about the analysis that we're doing for the retention side of it. So I guess a lot of retention talks that you see and a lot of companies out there that help you understand customer retention all seem to be based around like a very like classification view of retention, right? You're like looking at the chance of somebody making it to the next order, or trying to identify people that aren't going to carry on after their free trial, things like this. And these are all really useful, and we also have models like this working in tails, but they don't really tell us, it's very much like the binary outcome of are you going to order or are you not next month isn't really indicative of how long we think you're going to be a customer, which is really what we care about with lifetime value. So what we need is a more like regression-based approach, essentially, which is where survival analysis comes in. So what is it? Okay, well, let's get with a quick motivation, and a question that sometimes I do get asked at Tails as well, is like, okay, well, what is the average subscription length? Like, how long are people customers of Tails? And so, okay, let's take, say we have 9 pets here, and then these bars are tracking their average subscription length. The green bars are the pets that are still active, and the red bars are the pets that are no longer active customers of Tails. So you say, what's the average subscription length? It's like, well, what if I just take the average of all of these times? And you're like, well, that's not really fair because a lot of these people are still active, and if I do this again next month, I'm going to get a totally different answer because it's a moving target I'm essentially trying to look at. So I'm like, okay, what if I just ignore the active people and just take the inactive people and look at the average of them? And you're like, well, no, not really, because again, like some people become inactive and that will change, and also you're massively biasing your data set to the people who've already cancelled. So neither way of taking a straightforward average really gives you what you want. And the reason for this is because we've got censored data, where we have data where we haven't actually observed the endpoint that we're trying to measure yet. So essentially taking an average like this is never really going to be a sensible thing to do. So we need survival analysis to try and overcome this problem. And this is kind of the study of estimating the time to an event for a particular population when you may not have all, seen all the events happen with all your data points. So where is it used? In fact, it's it's quite an old idea in statistics, and it's used quite a lot. So, for example, in medical statistics, not a very cheery example to start with, but if you're looking at survival rates after cancer and the probability that people are surviving 5-10 years, this is all survival analysis that's used to do this. If you're buying life insurance, essentially your premium is determined on how long the actuaries think that you've got to live, and so therefore how much they can afford to sell you life insurance for. But going back to what we care about is our customers and our dogs. And what we're looking at is from when customers have signed up and started, moved off their free trial onto paying for orders, how long do we think they're going to be open to receiving more Tails food, which obviously then goes into the lifetime value side of it. So I'll just start with a few definitions, so a small mathsy slide. So we'll take capital T. We'll take this to be the time to a subscription end for a customer. So it's obviously greater than 0, but it could be infinite if the customer never churns. And the quantity that we care about, and the thing that's going to help us understand lifetime value, is the probability that the customer hasn't churned at any day t into the future. And this is a a non-decreasing function. Maybe because, sorry, non-increasing function. But so we have the overall probability, but what's also important here is what's going to happen on each infinitesimal day. We define this by the hazard function, which is the probability that on any given day t, that this is the day that the customer churns, not one day before, not one day afterwards. And actually, these two things, I mean, as you expect, are related, but with just like a little bit of elementary probability, you can show that essentially the survival function is expressed in terms of the hazard function in a relatively simple way. And so far, I've not really told you anything about what a hazard function might look like or a survival function. This kind of holds for any expression or interpretation of survival function and hazard function to here. So, this is also quite a cool, nice general formula. So, a few package options. So, I've been mostly doing this in Python. So, in Python, you've got two main package options. You've got lifelines and scikit survival. So, lifelines is kind of a longer standing package. It's very, very lightweight, and both of these are based on scikit-learn, so you can use them how you'd use any scikit-learn package and put it in pipelines and stuff like that. But yeah, lifelines, again, it's got basically one job, which is to do survival analysis, so it's very, very lightweight, and so it's quite quick to start using it. And it's got really nice visualizations of everything that's going on. The only thing is that it only really covers linear models for survival analysis. So if you want something a little bit, more robust, yeah, So that's what I'm using here. So yeah, but it's a good, easy one to get started with. And if any of you were at PyCon last year, Sebastian Polsdale gave a talk on his PhD project, which was making scikit survival, which is a really good extension to lifelines. And this, again, it's built on the whole scikit-learn infrastructure, and it's got a lot more options of linear and non-linear models that you can use, and so you can do a lot more detailed analysis in there as well. So yeah, two really good options. There's also R, because again, it's a long-standing technique in statistics, so there's actually quite a lot of R packages that do both linear and like ensemble-based methods for looking at survival analysis. And there's also a lot of tutorials and lectures on the subject, and a lot of these tend to follow a data set and a package in R, so it's like a good way to learn a theory maybe if you're used to using R. Personally, I learned Python before R, and that's kind of where my preference is, so I find switching to R, it's like a little bit slower to train and everything like that. And also our stack at Tails is Python-based, so that's obviously biased to what I use there. But yeah, there's quite a lot of options out there for doing this kind of stuff. Okay, so how do we do the modeling? So, as I said before, what we care about is this quantity S of t, the survival function for a customer, and the probability that they're still a customer at day t. And we can't, in practice, just know this function because of our censored data. So instead, what you can do to estimate it is use a Kaplan-Meier estimate of the function, which is essentially built up like it's a product of, essentially a product of the ratio of the pets that have been allowed to get to that point, as in we've had enough data on them that they've reached day t, and then a ratio of the total that there were and the ones that churned on that day. And so, it's built up basically as a step function, which gets, the steps get infinitesimally smaller the more data that you have. And again, just using Lifeline's package, it's pretty simple just to drop this in. So here's just got a loop. So for a few of our promo groups that we have, let's look at what the survival curves look like and plot them. So when we run this, we get a graph that looks like this. And you can see I've got some confidence intervals here, so it's getting a good approximation of where the true survival curve would be in this data. So first off, now we can finally answer the question, what is an average subscription length for a customer? So to do this, we're essentially taking the median time that a customer is expected to be to survive until. So essentially reading off where we're 50% on the probability they're still a customer, and this tells us the expected number of days that you in this survival curve, we think you're going to be there. And what you can also see is there's quite a big difference between all these curves, because as it turns out, how you find us at Tails and how you become a customer gives us quite a lot of information about how much we think that you're joining Tails because you really, really love the service, and you've thought hard and this is like the best food for your dog, and joining it because you read about it in a magazine. You might have a different experience of Tails when you join. And so things like this we can see really, really impact our expectation of how long we think you're going to be a customer, which in turn influences your lifetime value. So what we can do as an extension to this then is essentially build a regression model where we're trying to estimate your survival function based on all of the factors that we know about you. So the model that is chosen, one of the options, and I think probably the most well used still, is the Cox proportional hazard model. And so if we remember our survival function as expressed in terms of our hazard function like this, the Cox proportional hazard model says, gives like this expression for our hazard function. And so why is it called proportional hazards is because for each two pets, for like any two pets at a given point in time, the ratio of their hazards is constant, because all of the information in how the hazard changes over time is encoded in a baseline hazard function, lambda 0, and the impact that all of the features, like promo channel that I've just showed you, any other features that you can think about that we might put into this with our customers and our dogs, are encoded as this kind of like constant term on the side, which is, has a constant impact on the hazard over time. So there's a little gotcha there. So again, it's the most well-used one, but the fact that the impacts that you're having are constant over time, might not be true. And there's kind of quite a lot of factors that you can think about putting in here which would violate this assumption. Something like, I don't know, the total amount of like refunds you've had over time, for instance, that would vary. So the quantity would vary and then have like a varying impact on the survival over time. So it might not be a sensible choice just to throw into the Cox model. But then obviously there's a lot of things that are, constant over time, which we know about you from sign up and the consultation of signing up. So these are the type of features that we want to use in a model like this. So yeah, essentially it's everything we know about you when you sign up, about your dog, about you, like where you came from, whether you read your first email, those kind of things. And also some stuff that you've done in trial that's kind of things that we can take into account before we start modeling you and your lifetime value and how long we think you're going to be a customer. So yeah, a little bit on feature engineering then, because I feel like it's not a proper data science talk unless we talk a bit about feature engineering. But we got a lot of categorical data. So particularly stuff like breed, where it's kind of high cardinality categorical data. So we've got a couple of options about how we can encode this. So kind of a standard one-hot encoding approach where you just turn it into like n or n-1 binary features based on all of the breeds. This would be great for X. If you remember how our Cox model looks, it means we'd have a coefficient attached to every single breed, so you'd get really good clarity on how the difference between all of the levels of your, between all of the categories actually relate to each other, which is quite cool. But you're going to end up with a massive data set. Obviously, you've got the curse of dimensionality. Most likely, this isn't going to be the best way to get a really, really accurate result out of your model. So another one which I tend to use is basically keep it as one feature, but assign it a sensible ordering. Because again, we're in the world of essentially a linear model here. I can't just label them 1, 2, 3, 4. That kind of doesn't make any intrinsic sense. Instead, what I do is label them by like the sort of the median time that breed has been active, which I get from the Kaplan-Meier fitter process before, where we can, work out the average time, the expected time that each breed is going to be a customer, and then we feed the model this instead of the actual breed or some other labeling, and that gives us, it doesn't give us sparse data, and it also gives us a sensible ordering, which is like a little bit better and a little bit more powerful than just linear ordering like that. But I guess the downside is you don't get the nice interaction. You can't really as clearly see the relationship between all the different breeds. You just see breed as one feature. All right, so I was saying if we're doing a Cox proportional hazard model, we fit it in a relatively simple way, and then the summary result we get would look something like this. So here we have down the side just a few of the features that we put into it. And then you can read off the coefficient, the exponent of the coefficient, which is ultimately the thing that you're going to be multiplying your hazard rate by. So this is the quantity that really tells you the impact that this feature has, and then how confident the model was that it managed to find the right fit for this particular feature. So we can see second one down, email engagement factor. It's got an exponent of 0.63. And so the exponent, the further away it is from 1, the bigger the effect that this coefficient is going to have on the survival function. And the lower the coefficient, it means it reduces the hazard rate. And so therefore, I expect you to be a customer for longer. If that makes sense. So for an email engagement of 0.63, the higher you score on this email factor, this is actually quite a strong indicator that you have quite a reduced hazard rate, and so I think you're going to be a customer for much longer than compared to if you had quite a low score on that. And you can see the top one is extreme food amount, it was about kind of how much we're giving you each month. It's pretty close to 1, which means it has basically no impact, and also the model couldn't really reliably find where this parameter lived. It was somewhere very close to 1 either side. So in reality, we just want to ditch this from the model because it's not really telling us that much, and it's kind of just noise. Cool. So that's how we make the model. How do we know how good it is? So we do this by something called a concordance index. And what it's essentially doing is it's kind of measuring the ordered pairs and how well that you'd managed to order each possible pair in your data set. So say we just put all of the predictions for the expected time that people are going to be a customer on a line, so they'd all be obviously greater than 0, distributed like this. And say we had 2 dogs, Mowgli, who was down here, and Mr. Patch here, both office dogs, by the way. And so let's see how the model managed to successfully order these guys. So if Mowgli was active for 12 months and Mr. Patch has been active for 18 months, for simplicity, we'll say that they're both now cancelled customers. And if my model predicted that Mr. Patch would be active for longer, and then correct, I get 1 point for that pair. If it predicted Mowgli would be active for longer, I get nothing. And then there's kind of like a normalized, basically, success score of how many ordered pairs we got right. And then the scoring kind of works the same way as like a area under the curve score. It's in reality somewhere between 0.5 and 1. 0.5 would be the same as if we just, completely randomly put everything on the board. 1 would be a perfect ordering of everybody in the pair. So obviously the closer to 1, the more accurate that your model is. Cool. So that's how we make the model, the Cox-Borgen hazard model. That's how we measure it. And then here, I've just dumped out like a random 1% or so of the pets that I was testing this on. And these are all their predictions for the survival curves. So you can see a couple of things in here. One, none of the lines are intersecting, which is good. Again, this comes from our proportional assumption because the shape of the curve is given by your baseline hazard function, and how that shifted up or down is relative to the features that I put in all of the input data about you. And then obviously we can read off what a happy customer looks like. We can read off what a not happy customer looks like. And then obviously, one, this gives us a prediction for you. And I have now an expectation for how long I think you're going to be a customer. And also we can kind of start to see what is it that makes a happy customer of Tails, and what is it that, where are people not really engaging with our service. And then obviously we can use that to try and improve retention and improve the offering for everybody, as well as getting the better understanding of retention and lifetime value. So that's all I've got to say. So as I said before, we are hiring. We've currently got a position for a data scientist, a full stack developer and a web developer. So if you like Python, data science, or dogs, and then here's my email, and there's our careers page. So check us out. Thanks. I can, just shout, it'd be fine.
I can just shout.
Yeah.
So I guess you've shown curves of survival rates based on assuming that customers are just doing what they will do naturally over time. So presumably you would use some of this analysis as inputs into models to try and drive retention programs or to understand where your internal processes are causing survival rates to drop off.
Yes, yeah, and in fact, actually, one of the, exactly that, which I guess I hadn't really thought about when I built this. It seemed to be, I was very much in the head of just trying to get something which we could plug into a lifetime value model. But in fact, the combination of features that we found from here and the characteristics turn out to be, when you combine them into kind of a survival prediction, like super predictive in other retention scenarios. So we're kind of using this very much as an input. If you could have essentially something that doesn't change, like from when someone starts a kind of predicted time that they're going to be active in loads and loads of retention scenarios that we're on different models that we're doing, this does also turn out to be really good, which was a nice bonus. Yeah.
It's perhaps a bit macabre, but you've been looking at your lifetime survival of your customers. Have you done anything to put bounds on the lifetime survival of the dogs themselves?
Great question, and kind of. We're sort of skirting it a bit at the moment because we're only like 3-4 years old as a company. But so I think one of the things we think about is we frame lifetime value very much as the customer, in the assumption that if you as a dog owner is a customer of Tails, and unfortunately your dog does die, and if you get a new dog, we'd like to think that you can also come back to Tails. But it's an excellent point, which I haven't got a smart answer in exactly how we're going to work out that, but it's something we need to think about.
Can you go back to slide 26?
Sure. That's very specific. Yeah, there we go.
Two possibly related questions. Can you comment on how you define a defection event, and can you comment on why there are kinks in these curves?
So what was the first bit?
Can you comment on how you define a defection event, how you decide when something
So for the first one, there's a blend of a few things. So if it's a subscription, so you can pause or cancel your subscription. So that's kind of obviously a signal that you don't want the food, but we usually, we define it as the time after you paused or cancelled and been inactive for sufficiently long that we don't think that you've got food at home, because some people will just do that as part of their daily, regular management of subscription. They don't like having stuff active. If that answer your question there. Yeah, and the kinks are essentially when we bill people. So these are our order times, effectively, because, you're more likely to do something when we remind you that we exist and that we would like some money. Yep.
Do you revise lifetime values as sequential data starts coming in?
Sorry?
Do you revise this data as, the customer behavior starts coming in?
So
Week or month?
so we weekly, actually how it works in production is we kind of use the survival analysis step to come up with great segments, like customer segmentation essentially, and the types of customers that we have, and then we kind of use those to sort of model retention off those guys separately. So there's sort of a level of abstraction. The weekly, when we update the weekly assumptions on the customer segments every week, and then this is kind of every couple of months or so, when we think that it might have changed how we're segmenting people, basically.
I was just wondering, the way you encode your pre's, are you introducing forward-looking bias then? Because if I understand that right, you're encoding it already based on your experience on how long a customer will survive, or that pre will survive.
Sorry, I don't think I got the first bit.
So aren't you introducing a forward-looking bias by how you encode your breeds? Because if I understood that correctly, you rank your breeds already according to how long experience you survive. They survive, right?
Kind of. I guess it depends on how you do it. If you have I guess, but also it didn't matter in that we kind of just cared how how much breed was a factor overall, rather than like, you know, again, because we're kind of using it to sort of understand the characteristics rather than like getting a reliable prediction on like the actual estimate of days. So I think I was happy with the fact that there's a little bit of encoding bias in there, if that makes sense. But it's a good point.
Have you used censorship in your data, and how did you manipulate censored
data? I used it in as much as like in the Cox model, it will take into account basically. Yeah, so we'd label essentially at the point where we aren't definitely sure that you're not a customer anymore, which is either that you're still active or that you had food sufficiently recently that we know that it's still possible that you're feeding your dog tails. So we basically encode that into as part of the fit. So the model does take into account. Yeah, exactly. So you have how it actually works in lifelines is you pass it a censorship column, which is binary 1 if the data censored, 0 otherwise. Yeah.
If you have a lot of re-engagement in your product, like returning it coming back, how do you build that into lifetime value?
So I suppose the lifetime value kind of acts as like an average over the point. So essentially, at the moment, we kind of, in the way we use it, we look at the lifetime value of the people that are still active. But if you're not active, you still kind of intrinsically have a value, so that we don't basically run into the issues where, you know, your value is 0, and then the next day if you come back, your value is like £100 over however long. So it's sort of, because we kind of take the lifetime value view is very much like from the day that you start paying, looking forwards, like how long, you know, how much value we think you're going to do that, and it's kind of like an average over everybody who was like you at the time. And so we just sort of kind of, we basically we still give you value, but we just kind of ignore you if you're not currently active.
So you mentioned when testing your model, you look at the sort of ordering of was everyone ordered correctly?
Yeah.
That then implicitly means that your sort of time is not relative to normal time. Like if it's the right ordering that everyone churns in like the next hour, then it's fine. But how do you still make sure that the lifetimes actually match up to like time we experience when people pay?
So I suppose, I guess we kind of do it from like, it's a good point, and I also kind of had this worry, but I think, and I don't know if anyone else knows of a way in directly from survival analysis that a different interpretation of what I'm about to say. But again, I guess because essentially we're essentially segmenting you by your position in like this ordering, and then we'll then kind of model your retention separately using like, you know, different analysis that we have. So that's kind of how we get the segments, and then we trace that back to like actually what you did, which is sort of how we overcome that. Yeah.
Have you thought, this is on a per customer basis, have you thought of linking it to customer profitability and sort of multiplying profitability or respect to profitability against the survival of the customer?
Well, I suppose essentially, I guess we kind of do that for the lifetime value, because your profitability is, the two biggest drivers, I guess, with the profitability is, with the overall value is like essentially profitability by each order and the retention. So we do have, you know, there's not a perfect correlation between our highest retained customers and our, you know, most value driving customers because of the order interaction within there. Is that what you mean? Yeah.
Thank you for this talk.
All right, thanks.